Imagine training a machine to generate perfect images, faces, landscapes, handwritten digits, by starting from pure noise and gradually transforming it into something real. This is the power of modern generative models like flow matching. But here's a deeper question. How do changes in the initial noise affect the final output? And more importantly, which parts of the noise actually cause changes in which features of the image? In this video, we dive into a powerful new method for uncovering the hidden causal structure inside flow matching models. We'll explore how Jacobian-vector products, mathematical tools from calculus, can reveal how tiny perturbations in latent space propagate through the model, shaping the final output in ways that go far beyond simple correlation. Let's start at the foundation. Flow matching learns a continuous velocity field that transforms a simple base distribution, like standard Gaussian noise, into a complex data distribution, such as real images. Unlike diffusion models that rely on noisy intermediate steps, flow matching works deterministically. It learns a time-dependent vector field v\theta, x, t, $, that guides each point from noise to data via an ordinary differential equation. \frac ddt \phi t, x, v \theta \phi t, x, t, \quad \phi 0 equals \text id. The optimal velocity field, derived from linear interpolation between paired samples, x0 sim p text init, and x1 sim p text data, $, is simply the conditional expectation of the trajectory difference. vxtt equals \mathb. This elegant formulation gives rise to a smooth, deterministic flow, one that can be integrated forward to generate new samples. But what happens when we nudge the input noise just slightly? What if we ask, how does a small change in the initial latent variable affect the final generated image? This is where Jacobian-vector products, JVPs, come in. A JVP measures the directional derivative of the model's output with respect to a perturbation in the input. For a trained flow f\theta, the JVP in direction z sim mathcolen 0, id, $, is approximated via finite differences. jf\theta, x0, z approx frac f theta, x0 plus \verpsilon z, f theta, x0, verpsilon. This gives us a practical way to estimate how local changes in the latent space affect the generated data, without needing to compute the full Jacobian matrix, which would be intractable in high dimensions. Now here's the key insight. The JVP reveals dependency structure. In synthetic experiments, we find that these empirical JVPs match analytical Jacobians exactly when the data distribution is Gaussian. Even more strikingly, in mixture-of-Gaussian settings, where the global flow is highly nonlinear, the local behavior remains approximately affine. That is, even though the overall transformation is complex, it decomposes into a convex blend of linear maps, each active in different regions of the data space. This means that local linearity is a fundamental property of flow matching, even when the global dynamics are nonlinear. The Jacobian isn't constant, but its variation comes from smooth transitions between different linear regimes, controlled by the posterior responsibilities of mixture components. Let's take this into real-world image data. On MNIST, we focus on the digit 5. Using a U-net-based flow model trained on 10,000 samples, we compute JVPs between pixel pairs, say, positions 148 and 15, 8, and estimate their correlation. The result? Our JVP-based estimator recovers a correlation coefficient of 0.867, compared to the empirical ground truth of 0.881. That's a remarkable match, despite using only a fraction of the data and no explicit training on correlation. But pixel-level dependencies aren't always meaningful. What about semantic attributes like heavy makeup, pointy nose, or rosy cheeks? To answer this, we compose the flow with a pre-trained ResNet 50 classifier. Now, instead of analyzing pixel perturbations, we analyze how small noise changes affect attribute predictions. The resulting attribute-level JVP estimator gives us a second-moment matrix of changes across the generated images. From this, we compute a normalized correlation matrix, just like we did for pixels. Now here's where it gets causal. In CelebA, we examine a hypothesized common cause structure. Heavy makeup may influence both pointy nose and rosy cheeks. If this is true, then conditioning on heavy makeup should reduce the correlation between the other two, because the shared variation is explained by the common cause. So we do something clever. We filter generated samples where the Jacobian norm of the classifier output for heavy makeup is near 0. This means that small latent perturbations induce minimal change in the classifier's prediction, effectively selecting samples where heavy makeup is stable or unresponsive. We then recompute the correlation between pointy nose and rosy cheeks on this filtered subset. The result? The correlation drops from 0.4 empirical to 0.04 estimated, a dramatic reduction. This is consistent with a common cause structure. But, and this is critical, this is not a true intervention. We didn't modify the generative process. We didn't set heavy makeup to a fixed value using a do operation. Instead, we conditioned on a subset of the data, where the model is insensitive to changes in that attribute. This is observational conditioning, not causal intervention. So while the result aligns with causal expectations, it doesn't prove causality in the formal sense of Pearl's structural causal model. It's a strong signal, suggesting that Jacobian-based filtering can mimic intervention effects, but it's not a replacement for proper structural manipulation. Still, this opens up a powerful new way to probe generative models. By analyzing how perturbations propagate through the flow, we gain insight into dependency structures at both pixel and semantic levels. And because JVPs are computationally efficient, especially with automatic differentiation, they scale well to large models. Looking ahead, several exciting directions emerge. From conditioning to intervention, can we modify the flow itself by adjusting the Jacobian of the velocity field to implement true do operations? Causal structure testing. Use synthetic datasets with known causal graphs, common causes, colliders, mediators, to test whether our method can distinguish them. Beyond Gaussians. Extend the local affine theory to richer distributions, or understand when Gaussian approximations hold. Counterfactuals. Move up Pearl's ladder to answer questions like, what would the face have looked like if the person had been wearing less makeup, but the nose and cheeks were unchanged? Scalable JVPs. Use sketching, power iteration, or randomized probing to reduce computational cost in high-dimensional settings. Disentanglement connections. Link this work to existing regularization techniques that promote independent latent factors via Jacobian control. In conclusion, flow matching isn't just a generative tool, it's a system with rich internal structure. By studying how small perturbations propagate through the flow, we uncover local linear behavior, dependency patterns, and even hints of causal relationships. JVPs give us a practical, interpretable lens into the model's internal dynamics. They let us ask, which parts of the latent space are responsible for which features? And while we're not yet doing full causal inference, we're taking meaningful steps toward making generative models not just powerful, but transparent, interpretable, and trustworthy. This is the future of AI, not just generating images, but understanding how they're built. Thank you for watching. If you found this insightful, hit like, subscribe, and let me know in the comments. What kind of causal analysis would you run on your favorite generative model? And if you want the code, it's available on GitHub, link in the description. Stay curious, stay critical, and keep pushing the edge of what AI can explain.